So it's my pleasure to welcome Karen Bryant. Karen is the Science Operations Center Manager for the Gold mission here at LASP. And she'll go into a lot of details about how the pipeline for the mission works. But she's been a critical part of setting up the SOC, as we refer to it here at LASP, and getting that up and running. And she's been very busy, and I appreciate her taking the time out of her schedule to present to us today. Part of the reason for that is because Gold has just this fall become operational, and they're working on all of the algorithms involved and all of the coding that goes into getting the data down, which is ultimately the goal of the mission. So I'll turn it over to you, Karen. And again, thank you for being with us today.
Thanks, Tom.
And I'm gonna switch sharing and you can start up your presentation.
All right.
And that looks great right there.
Okay, terrific. So as Tom said, my name is Karen Bryant, and this is a focus on the Gold ground system. So really we're going to focus on how the data gets from the Gold instrument to becoming publicly available science data products. Sorry, let's see. Okay, so GOLD stands for Global Scale Observations of the Limb and Disk, and as the name implies, the instrument is looking at the Earth's limb and disk. The instrument is an ultraviolet imaging spectrograph, and the ultraviolet portion means that we're looking at the ultraviolet wavelengths from 131 to 160 nanometers. The GOLD instrument was built by the University of Colorado at Boulder's Laboratory for Atmospheric and Space Physics, LASP. And the images here on this slide, the one on the left shows the actual GOLD instrument before it was delivered to the spacecraft. So as it was built up here at LASP, that was the final build. The image on the right shows the GOLD instrument attached to the SES-14 spacecraft. And I will use my mouse and show you the GOLD instrument location here on the SES-14 satellite. So what we have here is a diagram, a cutaway of a single channel. The GOLD instrument has two channels, channel A and channel B. Based on the diagram, they are identical in terms of optical path. So this shows the light path that the light takes in each channel. What we have is we're looking at the Earth's atmosphere. The light from the Earth's atmosphere comes in, the light shade hits the scan mirror, reflects off the telescope through the slit mechanism to the imaging mirror, hits the grating where the wavelengths are diffracted so that way the wavelengths we care about, again from the 131 to 160 nanometers, those fall on the detector. Going back to the previous slide, I want to point out that we have these 4 feet, part of the GOLD instrument. They are mounted in a fixed manner to the spacecraft. So the instrument itself, the entire platform does not move. So we have some mechanisms within the detector cavities themselves that move. So we'll go through those now. Because we were looking at the Earth's atmosphere, we wanted to be positioned on the nadir deck of the spacecraft. And the nadir deck means it's pointing towards the Earth. So the portions that do move within each of the channels is the scan mirror. And what this allows is the scan mirror height is 11 degrees. So we're only able to see either the northern hemisphere or the southern hemisphere one at a time. So only half of the Earth is visible, or half of the disk is visible at a time based on the scan mirror location. The telescope itself does not move, but we do have a slit mechanism that moves. We have 3 slits. Only one can be in position at a time. The slits include a high resolution slit, which is 7/10 of a degree wide. So that would be the portion of the Earth's disk or limb that we can see. Again, 7/10 of a degree for the high resolution slit For the low resolution slit, it's 15/10 of a degree, or we can have the occultation slit, which allows 1 degree in. And I have upcoming slides which give an illustration of this, but we'll discuss that later. The imaging mirror does not move. The grating can move, but again, what happens is as we move it, the wavelengths will shift where they fall on the detector. So that way, if we get burn-in over time, because there are some bright lines, very bright lines within these wavelength regions, we can move those so that that way the bright lines maybe burn in at one location, but then we move the the grating, and the wavelength falls on a new region. So it can help prolong the life of the detector this way, or the usability of the detector. But we are limited to the number of movements we can make with the grating, because eventually the wavelengths would fall off the detector, the wavelengths that we are interested in. And so as such, we have the plan to really only move that grating once every 6 months, or maybe even less frequently. So for this talk, that part doesn't play in a role, but what will play in is the scan mirror and the slit mechanism. So as we talk about observations in the upcoming slides, keep that in mind, that these are really the 2 key mechanisms that we move for our observations. So GOLD is hosted on the SES-14 satellite. What's unique about GOLD is that it's the first NASA science mission that's a hosted payload. A hosted payload means that we are flying on a commercial satellite, commercial communications satellite. So with traditional NASA missions, the spacecraft is specific to that mission, designed with the science instrument or instruments in mind. So the advantage of being a hosted mission or a hosted payload is that the cost of the spacecraft isn't paid for entirely by NASA. SES needed the satellite to perform their commercial communications, and so from that, we only needed to pay a smaller portion of the cost of the satellite. Similarly, if it's a traditional NASA mission, the mission itself has to pay for the launch vehicle, as well as any ground station antennas that are necessary if they need to be specific to that mission. Again, the advantage with being a hosted payload is that SES needed to already pay for the launch vehicle, so GOLD just needed to pay for a portion of the launch vehicle. SES needed to have the antennas available for communications, so GOLD only needed to pay for a small portion of the use of that. And so there are real advantages of being a hosted payload. Again, you can see that cost is a real savings. The thing we had requested from SES when we were in negotiations is that the GOLD instrument did want to see a good portion of the continental US. SES had a satellite going up that needed to provide communications over Brazil. So we're located at a geostationary orbit at 47.5 degrees west, which is centered over Brazil. This gives us the GOLD instrument a view of the majority of the continental US, not complete coverage, but a good chunk of it. And there are other benefits to this location as well. So this worked out well for the GOLD instrument. So as I said, SES owns and operates the satellite. The GOLD mission is responsible for operating the GOLD instrument. SES-14 is an Airbus Eurostar 3000 and launched from Kourou, French Guiana, physical location here, French Guiana in South America. It launched aboard an Ariane 5 launch vehicle on January 25th, 2018 at 7:20 p.m. It was a night launch, 7:20 p.m. local time, so it was a very beautiful launch. Pictures from launch here. SES-14 is using electric propulsion. So for orbit raising, to get from the initial geotransfer orbit, which the launch vehicle put us in, to reach geostationary orbit, we used electric propulsion. From the previous slide, you saw we launched on January 29th, but we didn't reach our geostationary orbit until July 16th. If you use traditional fuel propulsion or chemical propulsion, or rocket fuel burning, basically, it only takes about 2 weeks to reach geostationary orbit. So you can see from the end of January to July 16th, that took almost 5.5 months to reach orbit. So the trade-off between using electric propulsion versus chemical propulsion is that it takes much longer to get on orbit. But if you're willing to take that hit in the amount of time it takes to get on orbit, you see that you save 40% on mass. So when you launch, the amount that the launch vehicle providers charge is based on your mass. So being 40% lighter will save a significant amount. So fortunately, SES did a trade-off study for themselves to determine whether the cost savings was worth it compared to the additional 5 months it took to reach orbit. And for them, it was worth it. For the gold instrument, it was also a benefit because the longer we are in space, the more outgassing occurs, which means that there are fewer contaminants around before we powered on. Because we remained off during the orbit raising period, we had less risk of contamination by the time we reached geostationary orbit in July. So it was a real advantage for us as well as for SES using the electric propulsion. So as we said, SES-14 reached a geostationary orbit in July. Then throughout end of July and into August, SES spacecraft itself was commissioned. This involved performing checkouts of the individual subsystems on the spacecraft, as well as verifying that the antennas for the commercial communications were working. Then, once SES was commissioned, SES-14 was commissioned, we were able to commission the gold instrument. So we powered on the instrument on September 4th, 2018, and began commissioning at that point in time. For the instrument, it involved moving those mechanisms we discussed in the previous slides, where we moved the scan mirror, we tested out our slit mechanism, we also rotated our grating to make sure it was moving, verified everything was working. In addition, we verified that we were receiving all of the data we expect, the commands that we're sending are performing as expected. After we checked out all of our mechanisms, we wanted to take some baseline data for the science data. After we took the baseline data, this allows the science data to be trended over time. So if we see changes to the detectors or any degradation, because we perform these baseline observations during commissioning, the scientists have values to compare against, and so they can make corrections based on that over time. So we completed commissioning on October 16th of 2018 and then began nominal operations the next day. So it's been about 4 months since we've been in nominal operations. So we're approaching the time when we'll be ready to release our first public data products. This will be the level 1 science data products. And currently I haven't defined these data products, but I will define these levels in upcoming slides. We're targeting the release of these level 1 data products to the GOLD website on this Friday, March 1st. The level 2 data products really use these level 1 data products in order to make that product. And so because they need those products to the level 1 products to be stable and then to be able to test their algorithms based on that, they have an extra month before those data products need to be released. So the level 2 data products, we're targeting a release on April 1st. So now we're moving on to what the ground segment looks like. Because I'm here at the Science Operations Center, and that's currently the physical location. So behind me, the computers that you can see in the background, they are currently receiving real-time data from the GOLD instrument. Because I am specific to the SOC, from my perspective for GOLD, this is really the center of the universe. So we're going to start looking at the diagram from here at the Science Operations Center, or SOC, here in Boulder, Colorado. The SOC is responsible for instrument operations, which includes planning what operations will be performed on the GOLD instrument. Once we've developed our plan, from that we're able to generate the commands that need to be sent. So we generate a command file that we then send to the SES Satellite Control Center, which is located in Luxembourg City, Luxembourg. The Satellite Control Center, or SCC, is responsible for the spacecraft operations as well as sending those instrument commands to the GOLD instrument on board SES-14. So what you see here is that they have the ground station antennas here in Luxembourg. Then they uplink the commands to the SES-14 spacecraft. GOLD performs the commands, operations based on the commands, and generates the science data as well as instrument health and safety data. That data is sent down to the SES-GS GOLD ground station, or the GGS, which is located in Woodbine, Maryland. From there, the data is transferred back here to the SOC, where we monitor the data and produce a level 1 data product. I will get, again, in upcoming slides, we'll discuss each of the definitions for each of the science data levels. But for now, it's enough to say that then once those level 1 files are generated, we send that data to the University of Central Florida's Science Data Center in Orlando, Florida. They are responsible for generating the higher level data products, level 1B, level 1C, and level D, as well as the level 2 data products, as well as archiving the data for the life of the mission, and then distributing that data to the science data users, which includes the science community, the general public, as well as NASA's Space Physics Data Facility, or SPDF. Once the GOLD mission ends, the SPDF becomes the permanent archive, so that way the public still has access to the science data GOLD has collected, even after the GOLD mission is done being funded. Is there a question?
Okay. Not that I see yet, Karen. Thank you.
Okay. Sounds good. All right, then focusing in on the command link for SES-14, they use the S-band radio frequency for command uplink. So there are multiple bands for radio frequency for communicating with satellites. S-band is one of them. Each band has its own advantages and disadvantages. One of the advantages with S-band, one of the major advantages with S-band, is that rain or any clouds in the atmosphere do not have an impact on the signal, on the S-band signal. So that means even if it's rainy out, you have no problems getting these commands up to the spacecraft and to GOLD. This is very important because if there is an emergency or an anomaly on the spacecraft or GOLD, we're able to send commands in a relatively quick manner. And again, the importance of getting commands up is higher priority than any other consideration when you are talking about commands. The disadvantage of S-band is that you are very limited in terms of your data bandwidth or your data rate. And so you're limited to kilobits per second, which is still a significant amount of data that we can uplink. And the fortunate thing from the spacecraft perspective as well as the GOLD perspective is we really don't need to send a lot of commands, very large packets for commands. So the S-band works out very well for us. So following the command path, command files originate here at the SOC in Boulder. We send these command files to Luxembourg to the Satellite Control Center. They convert those files into a binary packet, and they apply the protocol that is necessary to transmit it over the S-band to get it from that ground antenna up to the spacecraft. Once it reaches the spacecraft routes that packet to the GOLD instrument. So this is a visual of the command data path where the command files originate here in Boulder, are sent to Luxembourg, where they are uplinked via S-band to the SES-14 spacecraft, which is located here at 47.5 degrees west. Because it's geostationary orbit, it is at the equator. Now moving on to the downlink side, we are using Ka band for telemetry. And again, for GOLD, what is involved for telemetry is the science data, as well as the GOLD instrument health and safety data. Ka band, just like the S band, has its own advantages and disadvantages. The advantage for Ka band is you can see that it's a much higher data rate. We downlink 6 megabits per second for GOLD, and that's a continuous stream. The disadvantage is that rain or clouds in the atmosphere do attenuate the Ka band. So what this means is that there are times when there's a major rainstorm at the ground station, or there's a major weather pattern, that our downlink can be interrupted. Because of the high data rate, we actually don't record the data on board the instrument, so that we are reliant on the real-time operation, or sorry, the real-time downlink. But again, the advantage is that with that Ka band, we are able to downlink at that high rate. So the trade-off study was done, and the higher data rate was way more important than the potential for the loss of the science data when there is rain. And over the course of the 4 months that we have been up, actually we've been, on for 5 months, considering it's September, we've only lost on the order of half an hour worth of science data over that entire time due to weather. So it's definitely a good trade-off in that respect. So on board, once the GOLD instrument has the commands, it generates the telemetry associated with that command, and then it routes the data packets to the spacecraft. The spacecraft then downlinks the telemetry through the onboard antenna, where it is received at the GOLD ground station antenna in Woodbine, Maryland. The ground station at Woodbine is in charge of converting the analog signal into a digital signal, so that way the data can be transferred via internet to the SOC here in Boulder. And this is the telemetry data path. So Ka band, down from the spacecraft to Woodbine. Woodbine converts those signals from analog to digital, where it's transferred here to Boulder. The next step in the chain that we're looking at is converting the telemetry to science data products. So the telemetry arrived as packets here in the SOC. The SOC converts these science packets that have raw values into a level 1A netcdf file. And the netcdf file contains converted values, or what we would call engineering units. So for example, the instrument would send down a raw value of 1234, and that's a data number, what we would call. That's not really in a human readable format. And so a conversion is applied to convert that data number into an engineering unit. In this case, it would be 5.1 volts. So that everything that's in the level 1A file is basically would be human readable now. Once that level 1A file is generated, the SOC transfers that file to the Science Data Center at UCF in Florida, in Orlando, Florida. And then the SDC processes that level 1A file into higher level science data products. As we discussed previously, now we finally see what these higher level data products mean. So level 1B converts that level 1A file, which has the counts from the detector in detector pixel space. So level 1B then needs to convert from pixel space into Earth coordinates, so latitude and longitude on the Earth. So that's the first conversion, the first mapping that's applied at level 1B. They still keep the full resolution in terms of each pixel. So at level 1C, what happens is those pixels are combined and binned to give a better signal to noise ratio. In addition, we apply calibrations and corrections at this level 1C. So background values are subtracted, and there are other corrections applied. As we talked about, we had taken during commissioning some baseline measurements so they can check for changes over time, and those type of changes are applied at this level 1C. Level 1C is kept in a data format, so it's very usable for scientists, but for, say, the average person who would want to look at what images has gold taken, level 1C is not your data product. They're usable by scientists and who convert them into their own plots depending on how they want to visualize the data. But the level 1D creates images of the level 1C so that way it makes it easier for the general public to understand. In addition, it gives the scientists the benefit of being able to quickly look at images and determine a specific date and time that maybe they want to download of the level 1C data product. The level 2 data products are daily files that talk about or that give information about the geophysical data of the atmosphere. So for example, one of the data products for level 2 will be O to N2 ratio. Another data product gives the temperature at the limb. So those are all of the data products. So now that we have that portion added, we can follow the end-to-end data path, where again, commands originate here at the SOC in Boulder. Files are sent to Luxembourg, uplinked to the spacecraft. Based on those commands, the instrument performs its operations to downlink telemetry. That telemetry is received at Woodbine and then sent to Boulder to the SOC. SOC converts that raw data into the level 1A format, transfers those files to UCF Science Data Center. So that's the end-to-end data path that our data follows. So now we'll look a little bit more at the science algorithms in the pipeline. So the algorithms themselves are the development is distributed across 2 teams. LASP is responsible for the level 1 algorithms, and the algorithms themselves are really the code that generate those data products, the level 1 data products we just discussed. Computational Physics Incorporated, or CPI, is responsible for the level 2 algorithms, and again, that's the code that generates those data products. The University of Central Florida, the Science Data Center, is responsible for 3 parts of the science data: the processing pipeline, the archive, and distributing the science data. On the next slide, we'll cover the processing pipeline, but really that's the glue that holds it all together and generates the various levels. So let's look at that in more detail. What we have here in the legend, you see the blue bubbles are the code, and these rectangles with the tab are the actual data products themselves. Instrument generates the telemetry sent down to the Gold Ground Station. Gold Ground Station sends the level 0 data or the stream of data to the SOC, where the level 0 code is run in order to generate a level 0 file. That file is processed by the level 1A code to generate that level 1A netCDF file we talked about that has the engineering units as opposed to the raw data numbers. That file is then transferred to the Science Data Center at UCF. And then what's not shown is we discussed the pipeline, and really these arrows are what you would consider the pipeline. That's the code that calls the level 1D. It says, okay, now that I've received this level 1A file, I can call the level 1B code or algorithm to generate the level 1B file. And you can see there are various things that ephemeris data is the pointing information. That's how we are able to apply the location on the Earth to the level 1B data. We discussed those calibration files that are used for making corrections at the level 1C, when that code is called. And then you can see the level 1C, once it is generated, it triggers processing for level 1D, as well as on a daily basis, once all of the level 1C files are created for a single day, then the level 2 data products can be called and created. And what you see is that the level 1C, the level 1D, and the level 2 do become publicly available. We also then create level 3 data products, which are averages of the level 2 data products, and those will also be available on the web. So now we're going to talk about the ground system development and testing to basically describe how we got to where we are today. So the actual design work began in December of 2013 when we began our preliminary design. That took us about 1 year, where in December of 2014 we had a preliminary design review, or PDR. At that point in time, external reviewers were able to listen to our design of both the gold ground system as well as the gold instrument itself. Based on the comments from the reviewers, we took those into account and performed trade studies, and then continued through a critical design phase. So the critical design phase lasted from October 2014 until December of 2014 to October of 2015, and culminated in a critical design review, or CDR, in October. Based on that outcome, they said, you guys are ready to proceed on. The reviewers said, you are ready to proceed on with the development phase of both the ground system and the flight instrument. So then we began our development and test phases. So that after CDR, during this time frame between October 2015 and June of 2016, we really began to develop the ground system, and we built the flight instrument. Once the flight instrument was complete, we were ready for pre-environmental review, or PER, in June of 2016. That meant that the flight instrument was ready to perform instrument standalone testing, and the ground system had enough a development where it was able to support these tests. We continued, though, with ground system development throughout and instrument testing from June of 2016 through November of 2016, when we had our pre-ship review, or PSR. The PSR meant we had completed our environmental testing of the instrument, and we were ready to ship the instrument to the spacecraft facility. Airbus is located in Toulouse, France. So in December of 2016, the gold instrument was shipped to Toulouse, integrated onto the spacecraft, and then in January of 2017, the spacecraft repeated the similar type of environmental testing that the instrument went through, but this time it was the complete spacecraft that went through those type of tests. Those type of tests include thermal vacuum testing, vibration testing, electromagnetic interference, and electromagnetic conductance tests to simulate the environment that we see in space. So the other thing that, besides the spacecraft testing that went on, is we were also able to perform ground system testing during this time frame. So throughout, again, basically from October 2015 until December of 2017, we were able to thoroughly test out the gold ground segment. So then we had to have ground segment testing done before the Operational Readiness Review, or ORR, that was held in December of 2017. And that was the gateway that said, we are ready to support flight operations. So here's a more detailed look at how we tested the ground segment. I did mention in the previous slide that a lot of instrument testing and environmental testing went on, and that's not the focus of this talk. So again, we're really only focusing on the tests that the ground segment went through. You saw this slide earlier, and this is the same. These are really all of the interfaces. These arrows that are now colored are really the main interfaces that we needed to test for ground segment testing. Over the course of 5 tests, we were able to test all of these interfaces. These colors correspond to the tests we ran. So you can see that we performed 2 SOC to SDC tests in February of 2017. We tested that interface just to make sure that we could send data back and forth, and that way we could verify that the network was up and we verified the processing pipeline. So remember in the slide we showed previously that went through each of the algorithms and how level 1A generates the level 1B data products, and feeds into that. The pipeline itself, which were the arrows, was tested, but we didn't actually test the algorithms. So in November of 2017, we added the piece that tested the algorithms as well as reprocessing. One thing that happens over the course of a mission is the gold instrument has a 2-year primary mission, but assuming things go well after the 2 years, we hope to get an extended mission. There are many missions and instruments that go well beyond a 10-year mission. And so reprocessing becomes critical, because if it took you a full day to process a day's worth of data, it would take you 10 years to reprocess a mission that's lasted 10 years. So from the reprocessing side of things, we want to make sure that we're able to process, and in this case, we have 4 months worth of data. As the mission progresses, the algorithms are refined, and so it becomes critical to be able to reprocess that science data in a timely manner. And so this reprocessing test was a key thing that we tested in November of 2017 to verify that we could reprocess multiple days worth of data in a single day. So again, all of those interfaces were tested, and then we were able to test the gold ground station to SOC connectivity in the network in October of 2017. In November of 2017, we tested between the satellite control center and the SOC, both the network and the interfaces. So that was a fairly straightforward test. And the items listed in purple for the SCC SOC compatibility test, we really were able to test the interface between the SOC, the satellite control center, but also at the time, the SES-14 spacecraft was still at Airbus on the ground, and so we weren't able to test these antennas, which were tested in a separate test, but we were able to test the link in this end-to-end fashion. SOC sending the command files to the satellite control center sending commands to the SES-14, which was located at Airbus, and then the SES-14 sending data back to the gold ground station. So that was a very thorough test we were able to perform in November of 2017. Again, we really couldn't test all of these features in the end-to-end manner, like all during a single test, but between the 5 different tests, we were able to test the entire ground segment in an end-to-end fashion. So now we're going to talk about the actual observations and planning that goes on for the gold instrument. So as we discussed previously, SES-14 is in a geostationary orbit, and gold itself is mounted on the nadir deck of the spacecraft, which again means that per this dotted line, that's the instrument field of view. So geostationary orbit means that we are these spacecraft orbits over a fixed location on the Earth. As we discussed, it's at 47.5 degrees west, 0 degrees at the equator in latitude. And what this means is that as the Earth orbits throughout the day, the gold instrument, the SES-14 spacecraft stays over that same point. But what this means for the gold instrument, because it is looking back at the Earth, there are specific times every day when the sun is in the gold instrument field of view. This is a problem for our detectors because we aren't designed to be looking at the sun. We're designed to be looking at the radiation that's coming off of the Earth's atmosphere, which is way lower intensity than the sun itself. So in order to protect the detectors from during this time when the sun would be in the instrument field of view, we do put we turn the detectors off, we turn off our high voltage, and we put the instrument into a solar safe mode. This plays into what we're talking about here, which is this timeline looks at a typical day in the life of the gold instrument. So starting here at 0040 UTC, which converts to 2230 spacecraft local time, we do put the instrument into that solar safe, which is a continuation of that slide from the previous slide we just looked at. So the instrument is in solar safe from 0040 UTC until 0510 UTC every day. One thing that we talked about previously as well is that for the S-band commanding, we do have a does have a limited data rate, and so because of the allocation that SES has given us in terms of how many commands we can uplink per week, we have that as one consideration. And then onboard the gold instrument itself, we have a limitation of how many stored commands we can hold. We like to send a full week's worth of commands on a weekly basis. So we only really need to send 10 minutes worth of commands per week. And so in order to optimize that, because of these two, not so much limitations as much as constraints, we've broken up our operations into 30-minute chunks because that helped us optimize all of our commanding. And so everything you see then outside of our solar safe zone is broken up into 30-minute chunks. What you see is at 5:10, we turn the detectors and the high voltage on. Again, that allows them to warm up. And then we're able to perform our flat field operations beginning at 0540 UTC. What the flat field operations do is allow us to track any changes to the detectors over time. They have the flat field is an LED that gives us a repetitive form for seeing changes in the detectors. Then what you see is from 0610 UTC until 2010 UTC, we perform one of two types of 30-minute observations. We do a dayside disk followed by a limb scan, or we perform a disk scan interrupted by a stellar occultation and then resuming with a disk scan. So those are really the two types of blocks that we perform throughout the day. Then beginning at 2010, Channel B transitions to taking night side disk scans and performs that until we need to enter solar safe mode again at 0040. Channel A continues to take dayside disk and limb or disk and occultation observations until 2310, at which point it transitions to taking night side observations. So let's look at each one of these observations that were just described. This is what the day disk scan looks like. We talked about this is the location of the spacecraft, and this is the field of view for the gold instrument. You can see, like we talked, we don't have the entire continental US, but we have the majority of the continental US in our field of view. As we talked about then, when we talked about the actual light path of each of the detectors, we talked about the two mechanisms that are involved. The scan mirror, which provides the location in the northern hemisphere as it steps. As the scan mirror steps, it will take each of these positions. And the slit mechanism is the other thing we discussed. What this is illustrating is the high resolution slit. Really, that's the portion, as we talked, that was 7/10 of a degree. That's the portion that you can actually see per image that we take. So what happens is, it takes 12 minutes. We move the scan mirror to the eastern limb of the northern hemisphere, and then we take 12 minutes to step across the entire disk till we finish on the west limb of the northern hemisphere. So that's a single disk scan that takes 12 minutes, and then the mirror is moved to the east limb of the southern hemisphere, and we step across, and that again takes 12 minutes to get to the western hemisphere. So what you can see is that to perform per channel to perform a full disk scan takes a total of 24 minutes. So out of that 30-minute block we had talked about, and in the planning slide, we've covered 24 of that 30-minute block. So we mentioned that you can either follow that by a limb scan. Here's what the limb scans look like. In the morning, before noon spacecraft local time, the sun is over here on this side and illuminating this portion of the limb. So for a limb scan, we start at 50 kilometers below the Earth's surface and scan out to 430 kilometers. And that's the measurement at the equator, because you can see, because Earth is round, or oblong shape, the elevation here at this latitude is more than 430 kilometers. So that's why we're measuring that at the equator. So what we do, again, we move that scan mirror to this position on the northern hemisphere on the east limb, again using the high resolution slit, and we scan, in this case, from west to east to go from just below the surface of the Earth to that 430 kilometers. That step of observations takes 3 minutes. Then we move the scan mirror to the southern hemisphere and perform that same observation for 3 minutes. So that gives you that total of 6 minutes to fill out that 30-minute block. In the afternoon, we just perform the same operation on the western limb, since that is the portion of the limb that is illuminated by the sun. For occultations, what we do is we start our scan, our disk scan, when the star would be available. We pause the disk scan. We change the slit to the occultation slit. So again, that slit is 1 degree wide. And we move that we move the mirror to the specific location where the star will pass through that field of view. So the mirror is then centered at 225 kilometers above the surface where the star intercept will be. We park the mirror there, and it takes 4 minutes for the star to move 1 degree. Since the occultation slit is 1 degree wide, we actually allow for a 5-minute observation. So we're giving ourselves some buffer for any timing errors. Then we just park, let the star drift through our field of view. Once that 5-minute dwell is complete, we return the slit mechanism to the high resolution slit. We return the scan mirror to the position where it finished or where it paused prior to the occultation, and then we resume the disk scan. So again, within a 30-minute block, we have the 2 12-minute disk scans plus a 6-minute occultation, which again then fills out your 30-minute block. Night scans still stay within those 30-minute blocks, but they last for 15 minutes each. What we do is we use the low resolution slit, so that one's slightly wider than the high resolution slit. It's 15/10 of a degree. We move the scan mirror to the dark side of the terminator, and then we scan from west to east. So depending on season, these will change throughout the year, because sometimes towards so the solstices, the northern hemisphere or the southern hemisphere will have the terminator location of the terminator changes throughout the year. So we have those optimized based on the location of the terminator throughout the year. So these scans are optimized for that. Okay, and so then from that, let's now look at the gold data products themselves. So this is a look at the level 1D images for each of these type of scans that we just discussed. So this is what a disk scan looks like. As we talked, these because we scan first the northern hemisphere, then the southern hemisphere, they're separated by 12 minutes. If we were to try and put both the northern hemisphere and the southern hemisphere scan together, what would happen is where the terminator is would look like it had shifted. And of course it has, because they're separated by 12 minutes. In order to not cause confusion, we don't stitch those two together, we leave them separate. So that's why each of the hemispheres are individual in these level 1D data products. What you can see is this image was taken at 0740 UTC, which translates to 4:30 spacecraft local time. So you can see kind of over Brazil, it's still dark because it's 4:30 a.m., but you can see that the eastern edge of the Earth's disk is illuminated, and that is what you see here. You have various wavelengths that are covered here, 1356, LBH stands for the Lyman-Birch. Sorry, I had that documented. I have to look that one up. But that's a different wavelength region. So you can see that the radiation or the radiance at those different wavelengths is different. This is what our level 1D limb scan looks like. As we discussed, you start at the 50 kilometers below the surface and then scan out. And again, these are at the different wavelengths, the 1356 and the LBH. That's the radiance at those levels. For the occultations, you can see this is when the occultation enters the field of view. And then at different wavelengths, what the counts are. And then you see after 4 minutes, it leaves our field of view and we go back to being quiet. This one down here shows what the counts are versus wavelength. And then a look at a night scan. Again, limited to a single hemisphere. What you have then is you can see that in the near the North Polar region, you can see what the aurora looks like on that specific day that we took on February 9th of this year. All right, so that really wraps up the talk here. If you would like additional information or access to those level 1D data products that as they become available, scheduled again for this Friday, you can go to the GOLD website here. And then, as we said, the level 2 data products are currently not available, but they should be publicly available by early April. And that's it.
Okay, thanks, Karen. I did put into the chat that LBH is Lyman-Birch Hop Field. I'm sure everyone is waiting in great suspense for that.
Thank you.
Clarification. If anyone has any questions, you can enter those into the chat. We have a few more minutes before we're up to the hour. So feel free to type those into the chat and Karen will get to those as they come in. Karen, I had one question for you, and this is kind of an engineering question, but related to the reflection of the ray trace, that diagram you showed. Are there specific chemicals or metals or coatings that are put onto the mirror so that it only reflects in the ultraviolet, or in the specific wavelengths of ultraviolet, I guess, the GOLD is concerned with?
That is a really good question. I believe that the diffraction grating plays a large role in that, but those are details that I'm actually not very strong in.
Okay. I tried to add the disclaimer that it was a specific engineering question, but I'll have to check with one of our engineers on the team.
Yeah.
And we do have a question from one of the actual participants and not one of us here at LAST, but are we looking, and this is from Ed Wilson, are we looking at specific wavelengths like the hydrogen lines as they are intercepted by the Earth?
intersected by. So yeah, we can see a specific portion of the Earth's atmosphere, and I think depending on the wavelength, it determines the depth within the atmosphere of how deep we can see, and then they're able to look at those specific emissions. Does that answer the question?
I think so. And my understanding is that we are looking at specific wavelengths in the ultraviolet range. And then the 1356 is an oxygen line, not a hydrogen line. So these are, by intercepted, I guess those are absorption lines versus what's being reflected. Absorption spectra versus reflected spectra. And Ed adds, he's just trying to understand what kind of data are we looking at.
Yeah, my specialty, as you saw, was the ground system, and it's not really, my specialty is not the science itself. So I'm probably not the best person to answer a sciencey question.
Ed, I would recommend, if you're interested in learning more, we do have a full description of the science on the GOLD website, and I will just put that link in here again. Perfect. And I'll actually link you to our homepage rather than the webinar page. And then one of our GOLD team members also adds that we are looking at the nitrogen Lyman-Birch Hopfield spectra. That may not mean much to the lay audience, but if you want to follow up, you can check into that on the website as well, or get additional information on the website. Let's see, Oscar asks, any opportunities for citizen scientists to participate in the GOLD mission? Maybe related to the public data release, there's some opportunities there if you're so inclined at that level to work with the data products. I'm not aware of any other citizen science projects that we have ongoing. And then I don't know if you want to take this one, Karen, but can you briefly explain why the GOLD project exists and what benefits does it have, I guess, meaning for all of humanity?
Right. So one thing I can say is that the majority of the missions that have looked at the atmosphere, that as the GOLD instrument is doing, have been low Earth orbiters, meaning that they get just a slice of the Earth as it orbits. They can do 15 orbits in a day, but they get just a very small slice. The advantage for GOLD is that because we're in geostationary orbit, we get, within 24 minutes, we get full coverage of the portion that we can see. And so it's really nice that we can look at long-term trends and how the atmosphere evolves based on response from the solar input. And that's unique to GOLD because, again, the majority of previous missions have just had this small time slice of a very small portion of the atmosphere.
And one of the things that I'll add to that as well is there is a component of space weather involved in the science objectives of the GOLD mission. So we're looking at how the sun affects the Earth's upper atmosphere and how it responds to variable solar inputs. And so not only the atmosphere, but also our assets in space, GPS and radio communications and things of that nature are greatly affected by varying energy input from the sun. And so GOLD is it's not specifically a space weather monitoring instrument, but it does look at that effect in addition to the effect of the lower atmosphere, sort of the weather from below, and the effects that that has on the thermosphere and ionosphere as well. Let's see, we're pretty well out of time, but let me just see if we have, and Karen, you may not be aware of this either, but are there future missions that will use the hosted payload format or arrangement?
Yeah, so
I would guess that there are.
Yes. I know there's definitely another mission coming up that does a NASA mission that will plan to use that hosted payload format. I can't remember the name of the mission. I'm sorry.
Yeah, but Gold is kind of a pioneering mission in that sense. I think there's been one other payload prior to Gold. I don't know if it was a NASA payload. I don't believe it was a science payload.
That was an Air Force, and you're right. It was really just that one was called Chirp. That one I am more familiar with, and they were really just testing out the viability and seeing what the trade-off was. And from the Chirp studies that I saw, they saved $83 million by using the hosted payload model over procuring their own spacecraft and their own launch vehicle. Because it was Air Force, and they did want to have their telemetry downlink separate from the spacecraft downlink, so they actually did develop their own antenna systems or used existing antenna systems that were specific to the Air Force. So from that perspective, they didn't save on that portion of it, but they had a significant savings on the spacecraft itself and the launch vehicle.
And one final question, Karen, if you're okay, answering one more is, what are we doing, and I think you covered this, but specific things to protect the optics during sun safing? For example, turning the scan mirror away, perhaps?
Right, that is a good point. I did not mention that, but we turn the scan mirror. You can see here, we actually turn it edge on, so that way the edge would be the one seeing any light coming in, as opposed to having it be able to reflect all the way through. And as we talked about, we do turn the detectors off, and we turn the high voltage power supply off. One thing I didn't discuss at all is there is a solar safety sensor. It's right here. It's larger than the field of view of the instrument. So if the solar safety sensor sees an increase in voltage, it indicates that an increase in current. It shows that the sun is in our field of view. And the flight software takes automatic steps to safe the instrument, which means that if for some reason we weren't able to get those commands up to the instrument, the solar safety sensor would turn off the high voltage power supply and turn off the detectors. The thing it wouldn't do with the solar safety sensor is move that scan mirror to the edge on position, but we would still be safe because the detectors themselves are off and the high voltage power supply is off.
Great. Well, we're a little over time. Karen, again, thank you for your presentation. Really learned a lot, and I think everyone did. You're getting a lot of kudos in the chat. For those attending, we will process the video and post this on the Gold website along with the slides and the audio. So check back there if you're interested in reviewing this or using it for presentations through the Solar System Ambassadors program, and otherwise feel free to use those resources as you're able to. And with the end of this presentation, this concludes our series for Gold. I hope you enjoyed those, and you can check out other webinars at that same website. So Karen, thank you, and we'll be signing off.